Hey Royals, in today's lesson, we're going to look at magnetic fields and we're going to draw some comparisons to our understanding of electric fields. So the first thing we're going to say is that when we dealt with electric fields, we introduced this idea that there's an electric field intensity, and we defined it based off of this variable here. Now, fields in general have these intensities. So when we talked about the gravitational field intensity, we used the small g with a vector above it. So naturally, when we talk about magnetic fields, it should also have a field intensity. And often we refer to it just simply as the field. And we denote it by the vector of a capital B. So that's going to be our magnetic field intensity. Now we measure this strength in units of Tesla. So let's become a little bit more familiar with the forces that moving charges or current can cause on wires. So earlier in your studies, or grade 11, you may have noticed that a current carrying wire produces a magnetic field around it. And we brought along a right-hand rule that helped us remember this. And I'll show you this right-hand rule again. Now this simulation has a loop of wire. As you can see here, this big black line, and then there is a piece of paper with some iron filings on it. Now, iron is magnetic. It will be influenced by a magnetic field. So what's going to happen is let's put a current into this wire. So as we increase the current in the wire, you may notice that these iron filings are becoming more and more circular in shape around this wire. So that begs the question, why are they going in this circular pattern? Well, the one thing we can do is we can grab a compass and we can put this compass on that piece of paper, and you can see it does in fact follow this circular path. So that's indicating to us that there is a magnetic field, which is our B field, that is circling this wire. Now the compass, remember, wants to point in the direction of the magnetic field. So the red arrow here is pointing in the direction that it sees as north. So it wants to point north. So if we were to take this and we think about our wire here, you can see that it does go around this current. And we're using the big red arrow here to indicate the direction of the current because it comes out this positive end of the battery, up through the piece of paper, and then back into the negative terminals of the battery. So the right-hand rule you may remember is that we're going to point our thumb in the direction of the current, and the way that our fingers would wrap around that wire would tell us the direction that the magnetic field is acting. Now, if we were to look at our note here, we can't really draw three-dimensional on a two-dimensional surface, being our piece of paper. So we often use these symbols that, the circle with a dot means the current, let's put this, current coming out of the page. And we often then say that the circle with the X in it is the current going into the page. Going into page. All right, so here we see that the current is coming out of the page at us on this diagram over on the left-hand side of our page. So that would indicate to us that we would put our thumb coming straight out of the computer screen at us, and our fingers would naturally curl around this wire in a counterclockwise fashion. Now what I've done here is I've taken that same picture and I've put it here on the right hand side of our page. So you can see the current is still coming in this counterclockwise, the current's still coming out of the page, and the magnetic field is still going counterclockwise. Now with a bar magnet or a horseshoe magnet, the field lines, these magnetic field lines, always go from north to south. Similar to how our electric field lines go from a positive charge or the positive plate, if we have parallel plates, to the negative plate. Now, I do not want you thinking that that means that north is the same thing as positive. It's not, because we're dealing with different types of fields. They just simply have that analogy that they act similarly. Okay, so what happens here? Well, that means if we were to focus just on these parts of the wire, you can see that the magnetic field line for the wire is going up, but the magnetic field lines for that permanent magnet, the north and south magnet, is going down. Now these field lines will compete with each other, and in fact they add to 0 at this point. So you end up getting that this side of the loops cancel out. Field lines, as you remember, indicate field strength. So the closer they are together, the stronger the resultant force that we might feel at that spot. We also know that electric field lines and magnetic field lines and even gravitational field lines, they don't like to cross each other. They actually repel each other. So that means that with this wire here, this magnetic field line acting downward, and this magnetic field line coming counterclockwise, they're going to repel each other. And you're going to get a net force from this side of the wire acting towards the right. And we just talked about how this side they cancel out, which means that the field lines will kind of push towards the right as well. And this is the case that we had the current and the magnetic fields perpendicular to each other. If we were to take both of these forces together, you can see that the resultant force on that wire is towards the right. And let's demonstrate this. Okay, so we're going to go to another simulation and demonstrate how we can come up with this same solution. So here we go. We have a loop of wire inside a permanent magnet. So this is a horseshoe magnet. So we have our north pole at the bottom, our south pole at the top, and we know that the magnetic field lines would go from, the north towards the south. So you can see here, if I rotate it, that indicates our direction of the magnetic field. So it's acting from the north pole to the south pole. Now let's introduce a current into this wire. So for our reasons here, let's say that the current of the wire at the bottom of this loop is towards the back. So you can see here on our hand, what we're going to do is we're going to line up our thumb in the direction of that current. So the current is currently going into the page here. The magnetic field lines we're going to use as our fingers, like our pointer finger, middle finger, ring finger, and baby finger. So you can see that they are pointing upwards on our computer screen. And this is the third right-hand rule. It indicates that the direction that the force would act between these two, counteracting magnetic fields would be the direction that your palm would face. So if we were to add that there, you can see that the force is acting out of this horseshoe magnet. So we have here that this loop of wire should be forced outward. And that's very similar to what we just found with our example in our notes, was that there was a net force on the wire that was placed inside this magnetic field. So we remember that this is going to be our right-hand rule that will help us determine the direction of our net force or magnetic force. So let's go back to our note. So here we go. There is that right-hand rule that we were just talking about. So if we were to apply it to this example on our page, here I'll make a circle around it or a square around it, you can see that if you were going to do this, your thumb should point out of the screen. And that's because the current is actually coming straight out of the screen at us. Our fingers should be pointing downwards on our computer screen. So now we should have our fingers pointing down, our thumb pointing out of the computer screen, and you should see that your palm is in fact being pushed this way. Towards the right should be the direction that your palm is facing. And that tells us right on. We know which direction the magnetic force would be acting on that wire. Well, current in this example is just the flow of electrons. And so we can actually take this and apply it to the flow of any particle. So if we remember this is where it says it right here, that the field, the size of the field and the flow of the current can help us determine that magnitude of the force. So the amount of charge that's flowing and how fast it is governs the current in the wire. Okay, so if I take this, I can kind of replace this piece here. This is just our current in the wire. That's your thumb. And we were to cross it with the magnetic field. That was our fingers. And that's what we were doing up here. That was our fingers was the purple and our thumb was that yellow. And when we did this cross product, we ended up with vectors that were perpendicular to each other. And I'll show you what I mean by that. So you always will end up getting 3 vectors that are perpendicular to each other. So you can see kind of on this screen right now that the current is going left to right, which could be like your x-axis. The magnetic field intensity is going upwards on our page, so that could be like the y-axis. And then the force would be in that z-axis, in and out of the page. And so you can see that no matter what I do, these 3 vectors are perpendicular to each other. So if I change the angle of the current, you can see the force, in fact, changes its direction too. So here I'll turn it so you can kind of see it. You can see that they always stay 90 degrees to each other. Same thing if I change the direction of the magnetic field, you can see that the force is always still 90 degrees to that field. Okay, so let's go back to our lesson. So with just using our right hand rule, we can determine the direction of that magnetic force by using this right hand rule number 3. Okay, now cross product, as you'll learn in calculus class, a cross product can be done if you know the components of each of those vectors, or simply you can do it by the sign. Instead of having that cross, the sign of the angle between the vector tails. So I've given you an example here. I want you to pause the video in a second after I've explained it and give it a shot. So we are going to always line our vectors up that the tails of the 2 vectors, so the V vector and the B vector, we line them up tail to tail. So you can see here, tail to tail. And once we've done that, you're going to take your fingers, you're going to point your fingers. That's my ring finger, my middle finger, my baby finger, all in the direction of that first vector. And what you're going to do is you're going to curl your fingers. So you're going to bend your fingers towards that magnetic field. And whatever direction your thumb points is the direction that the force will act. So what I want you to do right now is I want you to pause this video and try that. Point your fingers in the direction of V and then bend them. Physically curl your fingers towards that B field. So as you do this, you'll notice that your fingers only bend one way, towards the palm of your hand. So that means that if we were to take our fingers and we point them along this direction, here I'll try to draw my hand. No, that won't work. We'll just leave it off. If you point your fingers along this V and you bent your fingers towards the B field, your force should end up being straight out of the page. Okay, so that gives us an idea of the direction of the force. The magnitude, how large the force is, can be calculated just simply using QVB, sine the angle between these 2 vectors. Okay, so let's try an example problem with this. So we have a positron, which is a proton, and we're sending it into an area of a magnetic field. And the magnetic field is 0.5 Tesla upwards. Okay, so what I'm going to end up doing is let's do it so that we can see this coming towards us. So we're going to look down on this picture. So that means that upwards is going to be straight out of the page. And I'm going to make this, instead of up, I'm going to make it out of page. And let's keep drawing our magnetic field. So it's many, many, many arrows. You know that it's not just one arrow. If it's a uniform field, these lines, there's more than just the one field line. And what I mean by that is I'll show you that simulation again. So what I'm saying is if you were to draw this and you had your field lines, you can see that it's not just one arrow. What I'm trying to draw is multiple of these arrows, and then there's multiple layers of them. Here it's only drawn one kind of layer, so you can imagine another line of green arrows and another line of green arrows on the left-hand side of it and another line of green arrows. And that's what I'm trying to draw in our diagram. So let's go back to our lesson. So there is our magnetic field. So we're going to take our positron. So let's draw a positive charge here, and let's send it into this field. And we're going to have it coming at a velocity of 4.0 times 10 to the negative 5 meters a second, and it's going to end up going east. All right, so the charge we know on it, the mass and everything. So let's go ahead and list all those things. So the mass of our particle is 9.11 times 10 to the negative 31 kilograms. The charge on it is 1.602 times 10 to the negative 19 coulombs. And what we want to do with this question is we want to try to find the radius of the circular orbit. So here we go. We want to find the radius of the circular orbit, and we want to find the force, the magnitude of the force acting on this charge. So let's go ahead and say we want to find the magnitude of the magnetic force, and we want to find the radius of this curvature. All right, so if we were going to look at this, let's go ahead and use our right-hand rule right now. So the B field, my fingertips, should be coming out of the screen. My thumb is the direction of my velocity. All right. So let's start by trying to find the direction that the force acts on this moving particle. So what we're going to do is we're going to keep in mind the equation for our magnetic force. It's going to be QV cross B. So let's go ahead and point our fingers in the direction of that V. So my fingers are now pointing towards the right on my computer screen, and we're going to curl them towards B. So we're going to curl our fingers. We're going to bend them towards the B field, which is out of the page, and you should see that the force that's acting on this is acting straight down on our computer screen. So the force is pushing our charge so that it bends in this kind of direction. Okay, so let's figure out how large this radius actually is. So let's say FM is going to be equal to QV. Now I'm going to use script V, B sine theta, sine the angle between these two vectors. So this vector is, for our B field, is straight out of the page, and for V it's parallel to the page. So theta is going to be 90 degrees. All right, so let's put our numbers in. So we get 1.602 times 10 to the negative 19 coulombs. V is 4.0 times 10 to the negative 5 meters per second. B was 0.5 Tesla, and sine 90 degrees. Now sine of 90 degrees is 1. If we put this all in our calculator, we find out that the magnitude of the force is 3.204 times 10 to the negative 24 newtons. So that answers the first part. Check. We know what the force's magnitude is. We need to figure out this radius. What is R? All right, so let's try this. We're looking for R. Well, it's going in a circle, which means that we're going to bring out our circular motion information. So we know that the magnetic force is the reason that our particle goes in a circle. So that means that our magnetic force is the centripetal force. The magnetic force then is going to be equal to mv. Well, let's bring out the v squared divided by r. We know what Fm is, so that's good. Let's rearrange for r. You get r is equal to mv squared divided by Fm, the magnetic force. And let's put in our numbers. So if we put our numbers, the radius, the mass of our positron is 9.11 times 10 to the negative 31 kilograms. The speed is going in circular motion, so the speed should be constant, 4.0 times 10 to the negative 5. Oops, shouldn't be negative 5. It should be, oh, it is negative 5, okay. Negative 5 meters per second. We're going to square it, divided by the force we just found, 3.204 times 10 to the negative 24 newtons. And if we were to do this, we find out that the radius is 4.5 times 10 to the negative 16 meters. So the radius is quite small. So we have our two pieces here. So there is our radius that we were looking for. So let's highlight that so that we know that that's our final answer. And we know our magnetic force is what we were looking for earlier. And there it is there. So we're just going to highlight that. I'm just going to color it in so that we know exactly what we're looking at here. Perfect. And what we want to do is I'm going to show you a quick simulation of exactly the problem we just did. So this website here demonstrates exactly what we're dealing with here. So dots mean that the magnetic field is coming out towards us, or if I change the magnetic field strength and I make it negative, you can see that there we go. The magnetic field is now X's, which means it's going into the page. So we wanted something that's coming out of the page. So let's go with, like, say 0.5. There we go, 0.5. We want our charge is going to be times 10 to the negative 16 coulombs. So I don't know if we can get up to it. Let's go with, say, 10 times 10 to the negative 16. The speed's going to be quite slow, so let's bring it down to, I don't know, say 5 times 10 to the 6. So let's go right down to 5 times 10 to the 6. And the mass, let's leave the mass where it is. If we were to shoot this into the field, we can see here, and sure enough, whoop, the radius is, we can have it show us the radius, 6 millimeters. So why is this the case? Well, the V is going this way. The magnetic field lines are coming out of the page. So if we were to take it and place our hand in the direction of the velocity, so we see that the velocity is towards the right, so our fingers point to the right on our computer screen, and we want to bend them in the direction of the magnetic field. So that's out of the page. So we're going to bend our fingers out of the page, and you should see that the force is pushing straight down. If you change your velocity to be this spot right here, you see that the force is always inward. If you change your velocity to be kind of towards downward and the magnetic field is still out of the page, you see that, sure enough, your force is always inward. Now, one last piece that we always need to remember is this. So we're going to go back to our note. So one thing we want to remember is this. Right-hand rules are for positive charges. If you're working with an electron, whatever the right-hand rule tells you, you're going to do the opposite. So what I mean by that is if this was a negative charge, so we're going to follow the right-hand rule. The right-hand rule says, hey, it's going out of the page. It actually is into the page as the direction of the force for an electron or anything that is a negative charge. Okay, so right-hand rules are for positive charges, not negative charges. You just simply follow the right-hand rule, but flip what the answer is. All right, so as always, if you have any questions, please do not hesitate to reach out to me.